Hey chemistry peeps, Jess McCartney here. So today we're going to talk about equilibrium reactions. So looking at these pictures here, this represents the rate of a forward and reverse reaction. This is what is happening when we have an equilibrium reaction. So sometimes when we have an equilibrium reaction, it kind of looks like nothing is happening. But looking at these pictures, this represents this. So there is something happening. But it's nice and even, so we don't really see it. So looking at the man going up the escalator, he is continuously walking, so something is happening. Same as the taps running, they're running continuously. And this is what's happening with equilibrium reactions, which we're going to look at further today. So we're looking at equilibrium reactions today, still in the same area study 2. How can the rate and yield of the chemical reactions be optimized? And the study design dot points that we're going to look at today is the distinction between reversible and irreversible reactions. We're going to look at the difference between the rate and the extent of the reaction. And we're going to look at the dynamic nature of homogeneous equilibria involving aqueous solutions and gases, as well as looking at how they're represented in concentration and time graphs. So far we've only looked at open systems. So like this, where matter and energy can be exchanged between the reaction that's occurring and the outside environment. So that's what's happening with these arrows here. So when we're looking at an equilibrium reaction, it's actually a closed system, so this one here, where energy can be exchanged as seen in the diagram, but matter cannot. So what that means is that anything that's produced in the reaction is trapped. And now this is important because that means that even though the energy can escape, so being exothermic, or energy can come in being endothermic, the matter cannot. And this means that we can actually have reversible reactions where the products that have been produced can actually combine back up and make the reactants that we started with. And we're going to look at that further. So it's important to note that not all reactions are reversible. There are some irreversible reactions. Even if you have the right conditions that could possibly make a reversible reaction, so keeping it closed, that it's not possible for all reactions. So when you are reacting reactants, they will be converted to products and there's no going back. That's the way it is, and it cannot be reversed no matter what conditions it is. So an example of this is when we combust fuel. Even in a closed system, which is pretty impossible for a combustion because it does make explosions, but even in a closed system, it cannot produce those reactants again. So in an equilibrium reaction, which we're going to talk a lot about, is that these are all reversible. And when you have specific conditions, you can favour each side of the reaction. So depending on what conditions you have will depend on what side is favourable. Like I said before, a closed system means that the reactants cannot escape. Now, because of this, those products that have been formed can form back to reactants and vice versa, and that can continue to happen as long as that there's different conditions being applied to the system. As soon as that the rate of the forward and the reverse reaction is equal, this means that we have now reached what's known as dynamic equilibrium. So it's like that man in the escalator that we saw at the start, that as he's continuously moving, but you can't see anything happening. So that's what's happening there. So the rate of the forward and the reverse reaction is like a balance beam. It's coming up and down, up and down, up and down, not really moving anywhere. When equilibrium has reached, the overall concentration of the reactants and products do not change over time. So once that equilibrium is reached, unless you change the system in some way, that will stay as is. So the example we're going to look at today is known as the Haber-Bosch process, and we're going to look at this example a lot through talking about equilibrium systems, and that's because it is a very common and well-known example of an equilibrium reaction. So in this reaction, we are reacting nitrogen and hydrogen, and it's forming ammonia. Now, if you are looking at the equation, you can see that you have 1 mole of nitrogen and 3 mole of hydrogen reacting. Now, based on the equation and the coefficients written, you should get 2 mole of ammonia formed. Now, no matter how long we wait, we will actually never get that full 2 mole of ammonia formed. And this is because equilibrium arises before that point. So you can see that in our reaction that's formed and what has been produced in the products is that you have 7.7 mole of nitrogen that's left once it's reacted. And you have 2.1 mole that's left of hydrogen that's reacted. So that means that not all of that has reacted to form the products. Now, if not all of it has formed the products, that means that not all the products have been formed either. So the maximum amount of products haven't been formed. And you can see here that actually 0.6 mole of ammonia is formed. And so at this point, when you have these moles that's been formed, that is when it's reached equilibrium. Now, it will not proceed past that when the conditions are as is. Now, we can push the reaction further, but as is, once equilibrium is reached, that's what's formed. And we will talk about how we favour right and left sides further on down the chapter. But for now, when we're looking at it, that's as much as can be formed. So now we're going to talk about the rate and the extent and the difference between it. So when we think about the extent, we're thinking about how much products is being produced, and the rate is how fast this can happen. Now, when we're looking at this, we're actually looking at the percentage yield of products that can be produced. As chemists, we want to know how much yield we can get at the end of the reaction and whether this reaction will be worth it. So when we're talking about yield, refers to how much product can be obtained in the chemical reaction we are doing. Now, generally, we calculate the yield using a percentage, and this is the formula here. So like any percentage, it's calculated the same way. So we are going to use the actual yield, so the mass that's been weighed at the end of the reaction. So the actual mass. And then we're going to divide it by the theoretical yield. The theoretical yield is what we should get, so the calculated amount that we should get at the end of the reaction. Now, this is obviously based about stoichiometry, so using those stoichiometry calculations. And like any percentage, we will times this by 100. Now, when we talk about the extent, we actually use what's known as the equilibrium constant. Now, this is the ratio of concentrations, all right? So we are actually coming out of the mole. So even though we will talk about the mole, the equilibrium constant is done in concentrations. So the products, the concentrations of the reactants and the products in the reactions, that's what we're looking at. Now, we can actually tell how much the equation has moved to the products compared to the reactants and vice versa based on how big the K value is, so the equilibrium constant is. So when we are looking at the K, that's actually looking at the extent, so how much it has been pushed to the right or kept to the left. So if our K value is greater than 10 to the power of 4, that means that there's significant concentration of products. So that means that the reaction has been pushed to the right, so to the product side. If the K value is less than 10 to the negative 4, that means that there is significant proportion of reactants left. So it hasn't really gone to the product side. So some products may have been produced, but there's more reactants in this reaction than products. If it sits between these two values, so between 10 to the 4 and 10 to the negative 4, then there's considerable concentration of both reactants and products. So it's quite equal in terms of where the equilibrium sits. Now, this is a nice diagram to chuck into your notes, just showing this on a visual aspect, what's happening. So now we're going to talk about dynamic equilibrium again. So when equilibrium is in its dynamic state, the forward and reverse reactions have not ceased, but are occurring at the same time, so simultaneously at the same time. And the rate and occurring at the same rate. So this means that the reactants and the products are in a perpetual tug of war, so going back and forth, back and forth. So like the man on the escalator, where he is continuously moving, that's what's happening in this dynamic equilibrium. Now, there are conditions that need to occur for the dynamic equilibrium to be consistent like this. So the first thing is that the amounts of reactants and products are kept constant, so nothing is added or taken away from the system. So as long as that's occurring, that dynamic equilibrium will continue. The temperature of the system must be kept constant as well. Adding temperature or taking away temperature of a system will push the equilibrium one way or the other. And we will talk about this in a further lesson. So it's important to know that that temperature has to be kept constant. And that is the same as pressure is kept constant, because the pressure will also change which way the equilibrium shifts. And we will talk about that in further detail. So let's look at an example. So we have N2O4 gas reacting, and it's breaking down to form NO2 gas. Now this is at equilibrium, and you can see with the color change what's occurring here. So we are starting off with a clear solution. Now as the reaction progresses, you can see that the color starts to change. So after 3 seconds we get this yellow color, and that means that some of that NO2 gas has started to be formed already. And you can see like the molecules here that are little, but you can see that we have some NO2 molecules forming here. Now as it continues to progress, so to the 8 seconds, that we have this darker color red, all right, and we have more of these NO2 molecules that are forming as well. So we can see that this reaction. Now, we have 3 hours that goes past, and you can see that it's the exact same color as the 8 seconds. So that means that at that 8 seconds point, so this point here, we have reached dynamic equilibrium. Now, as long as our system is kept constant, so all these things here are kept constant, nothing will change, and it will stay at that equilibrium, constantly going back and forth, staying at that deep red color, and nothing will change unless the system is changed. Now, looking at the extent of the reaction a bit further, different reactions will have different extents. And this is depending on what you are reacting, and also the concentration and the conditions that the reaction is put under. So different conditions will have different extents. So this is what's happening here. Now we're going to look at an example, and you would have seen this example in year 11 when we studied acids and bases. Now if you remember way back then, we spoke about HCl, so hydrochloric acid, being a strong acid. Now a strong acid completely ionizes, and therefore it reacts to a high extent, so it produces a lot of products. And you can see that we're looking at this as an equilibrium, but it's shifted more to this side of the reaction. And you can see here, this is what's happening. Now, when we have something like ethanoic acid, it is a weak acid. Now, if you remember from year 11 chemistry, that weak acids do not ionize completely. And so therefore, that they do not have a high degree or react to a high extent. So that means that lots of the reaction actually sits on this product side. And you can tell this by running a conductivity prac. So actually testing how much electricity is running through that. So if you have a greater number of ions, so like what's shown in the first HCl reaction, it will conduct more electricity. Where if you don't have as much ions, so if it's sitting in this reactant side where they're not in ionic form, it will conduct less electricity. So it's a very quick and easy way to see how the extent of the reaction has progressed. So when we are looking at equilibrium, there are different ways that we can display equilibrium. So we're going to look at 2 ways. We're going to look at concentration and time graph. And this is useful when we're looking at the individual reactants and products being reacted and produced. So how those concentrations are changing as they react and how they produce the products. The second way is looking at the rate time graph, and this is looking at the forward and backwards reaction and when they become equilibrium. And rate is really important to understand, because even though we can look at an equilibrium reaction and understand whether it will be produce more products or reactants, we actually don't know how long that would take. So the rate actually gives us that information. So looking at the concentration versus time graphs, what it is looking at is the concentration of the products and reactants over time. So we represent it by this graph here. So looking at an example. So this is the Haber-Bosch process again that we've already spoke about today. where we have nitrogen and hydrogen reacting to form ammonia. Now you can see that nitrogen and hydrogen are the reactants. So we're starting at 3 mole, like in the equation, 1 mole of nitrogen, like in the equation. Now as they react, obviously their concentrations have to decrease, and they will decrease in their ratios of the equation. Now, as they decrease, the products being formed would have to increase. And again, they will increase based on the ratio, so the coefficients in the equation. So you can actually see how much is being produced based on that. So the reaction rate versus time graphs, we're looking at how the rate is occurring for both the forward and the reverse reaction. So you can see that for the rate of the forward reaction initially decreases until the system reaches equilibrium, and the rate of the reverse reaction increases. So this is a nice graph showing this. So again, we're looking at the Haber-Bosch process. So as the reaction progresses, the rate of the forward reaction begins to slow. All right, so that's what's happening here. So we can see the drop, and then it starts to plateau off as shown here. Now this is due to the increased presence of products and the decreased amount of reactions. Now, because this is in dynamic equilibrium, the same thing needs to be happening with the reverse. And you can see that with the reverse reaction, the products are making the reactants, and they will eventually line up to be equal. And so as soon as this lines up, equilibrium has been established. Now this will continue to go and continue to be as is unless something is introduced into the system. If nothing is introduced, that line will just continually go, again in that perpetual tug of war of a dynamic equilibrium. So bringing it all together, what are the things that need to occur for a dynamic equilibrium to be established? So first of all, we need to have constant concentrations. So the reactants and the products need to be as is, and nothing is being added or taken away. The temperature must be kept constant, so that cannot change. Total gas pressure also must be kept constant. And remember that the reaction is incomplete. So for there to be a dynamic equilibrium occurring, that you cannot have the full products being formed, because you need to have that constant back and forth motion happening for it to be considered as a dynamic equilibrium. So a quick, easy way to remember this is this: const, temp, pressure, incomplete. So they're the 4 things that need to happen for a dynamic equilibrium to be established. So in summary, when we have a dynamic equilibrium, the following things need to occur. The amount of the reactants and products needs to be kept constant. The temperature of the system also needs to be kept constant, and the pressure of the system needs to be kept constant. When we're looking at the extent of the reaction, we can calculate how much product we're going to get, or how much percentage yield we're going to get, using the following formula, where we have the actual yield divided by the theoretical yield times by 100, getting into a percentage. And we can also predict how much of the extent of the reaction has formed based on looking at the equilibrium constant. So remember, if our equilibrium constant is greater than 10 to the power of 4, then we have majority of products. If it's sitting between the 10 to the negative 4 and 10 to the power of 4, then we have that equal amount of reactants and products. If it's less than 10 to the negative 4, then we have majority of reactants. Now we can represent equilibrium 2 ways. So it can be the concentration time graph, where we're looking at the concentration of the reactants and products, so the reactants decreasing as they react and the products increasing, and vice versa, depending on when we're looking at reverse or forward reaction. Now with the reaction time graph, it can be tracking both the forward and reverse reaction at the same time, and when they reach those equal points on the graph, that's when equilibrium has been established. What's coming up next is we're going to be looking at calculating equilibrium constants, which is 5b. I will see you then. Bye-bye.